have you ever wondered if you could build something not with bricks and mortar, but with pure math? A system that starts out as just a loose metaphor about shapes, but then transforms into this, unbreakably secure architecture. Well, that's exactly what we're going to unpack today. We're going to follow the journey from a simple idea to a trust-based engine, all proven by mathematics. Let's get into it.
This quote right here just nails the whole journey we're about to take. We're literally moving from describing things based on how they feel to defining them by what they mathematically are. This is that exact moment where all the vague, fuzzy ideas get locked into place with real, unbreakable rules.
So, here's our roadmap. We're going to see how we get from metaphor to math. Then we'll look at the grammar, the rules of this world. We'll see how it makes proposals and validates them, how it gets its own unique fingerprints, and even how it breathes. And then at the end, we'll step back and see the whole elegant machine we've put together.
All right, part one. This whole thing didn't start with some grand blueprint. It actually began as a set of really powerful intuitions. What started out as these geometric metaphors, well, it kind of accidentally grew into this formal, multi-layered system where every single piece gives you a distinct, provable guarantee.
And this right here, this is the golden rule. It is the one principle that guides everything else. The whole point of the system is to be able to grow without breaking. It can add new parts, it can connect to other systems, it can expand its whole world, all while holding on to its core identity. It's all about evolving, but without ever losing what makes it, well, it.
So how do you actually build a world that can follow a rule that's strict? Well, you start with a universal grammar, a foundational set of rules that defines every possible structure, every possible action.
And believe it or not, the entire system is built from this one simple idea, the simplex. Think of it like the ultimate Lego brick. A single point, that's a 0 simplex. A line connecting two of those points, that's a 1 simplex. And a face, which is basically a rule that closes off 3 points, is a 2 simplex. Now, this isn't just about drawing a triangle. It's about creating a universal language for structure itself. Kind of cool, right?
Okay, this is where the metaphor gets really, really clever. You're seeing words on the screen like tetrahedral, but we're not talking about physical shapes here. Think of these as the laws of physics for our system. They're the unchangeable hardware rules. So a tetrahedral rule doesn't describe a shape, it just means something like every part must be connected to every other part in the most basic way possible. It's like the topology of the hardware itself.
So if the Platonic rules are the hardware, then what's the software? Well, that's where the Archimedean class comes in. You can see on the table we've got transformations like truncation and expansion. These are just fancy names for safe software changes. Truncation, that just means safely removing a feature. Expansion, safely adding one. These are the software updates that can happen without ever breaking those core hardware rules we just talked about.
Of course, if you have software making changes, you're going to need a way to check its work, and that's the Catalan class. If the Archimedean class proposes a change, the Catalan class is its mirror image. It's the validation layer. You can think of it as the system's own internal auditor, making sure every single action is totally valid.
Now, for any of this to work, the system needs a superpower. It's called canonicalization. I know, it sounds complex, but the idea is actually super simple. It's just the process of making sure everything is written in the exact same way every single time. It's like alphabetizing your ingredients before you start cooking. By putting everything into one standard, normal form, the system guarantees there are no surprises. The same input will always give you the same output. It's the secret to its perfect predictability.
Okay, so we've got our grammar, our set of constraints. Now let's see how they actually power the system's engine, that core operational loop that lets it act and verify all in this constant, reliable rhythm.
This slide really shows the system's two-step dance. On one side, you have an Archimedean message, which is basically saying, hey, let's do this. It's a proposal to make a change. Then, on the other side, you've got the Catalan message, which acts as the auditor. It checks the proposal and says, yep, that follows all the rules. It's this constant rhythm of proposal and proof, of action and verification. And that push and pull is what drives everything forward.
So with a system this dynamic, how does it maintain a stable sense of self? This brings us to one of the most elegant parts of the whole design, how it creates a unique, mathematically provable identity for its current state. So how does it do it? How does the system generate this unique fingerprint? It uses this really clever mathematical tool. Now, don't worry about the technical name, Fourier form. What's important is what it does. It creates a special kind of identity that's both super stable and also composable.
which means you can combine the fingerprints of two systems and you get a new, totally valid fingerprint for the combined system. It's kind of like having DNA that can safely merge with other DNA.
And it's not a one-size-fits-all thing either. As you can see, there are actually two types of fingerprints. First, there's the global one, the O8, which acts like a universal passport. It's valid everywhere in the system. Then there's the local one, P32, which is more like a private key card for a specific club. It requires a shared secret, what they call a SALT, to work, which makes sure that identity is only valid inside that one trusted circle.
All right, now for what might be the most dynamic part of the system. We have the rules, we have the identity, so how does it all actually work in runtime? Well, it uses this constant cycle of expansion and collapse to guarantee stability even while it's in motion.
The formal name for the model is the circulatory projection runtime, but I gotta say, I love the metaphor they use for it. It's like breathing. There's an inhalation, where the system expands to do some work, and then an exhalation, where it collapses right back to a known, safe state.
So let's just walk through this loop. The system starts at I, its home base, its stable identity state. Then it applies an expansion operator, E, which moves it into this expanded space, S, where it can do complex things. But then, and this is the crucial part, it applies a collapse operator, C, which always brings it right back to that stable identity, back to I. So it can go out and do its work, but it can never, ever get lost. And why is that collapse so ridiculously reliable? It's because the operation is idempotent. Now, this is a critical property. All it means is that you can apply the collapse operator over and over and over again, and the result won't change after the very first time. This guarantees a stable, predictable return trip home, preventing any kind of error or drift from building up. It's the ultimate safety net.
Okay, so we've seen all the pieces now. The simplex grammar, the constraint classes, the operational loop, the identity fingerprint, and that breathing runtime. So let's pull back and look at the complete architecture that we've just assembled.
And here it is, the full stack. I mean, just look at this. Every layer, from the very bottom to the very top, provides a unique, unbreakable promise. You've got the universal language, the hardware rules, the software rules, the auditor, the identity engine, and the runtime model. Each layer builds on the one below it, not fighting it, but in perfect harmony. This is how you build a system that is profoundly, provably trustworthy.
When you get right down to it, all that talk of tetrahedrons and cubes, that was just a ladder we used to climb up to a much deeper principle. This architecture was never really about shapes. It is a masterclass in building systems that can grow, that can change, and that can connect, all while preserving their fundamental integrity.
So we end with this question. We've just walked through a system where trust isn't an add-on or an afterthought. It is literally baked into the mathematics from the very first step. It's not a promise, it's a proof. And if we can build systems like this, what does that mean for the future of trust in our digital world? What could that change?